Hello, thank you for your interest in our work. I'm Anil, presenting a closer look at temporal ordering in the segmentation of instructional videos. This work is done with Shreyank, Frank Keller, Laura Sevilla at the University of Edinburgh. First, we look at what is our task, that is, procedure segmentation and summarization. A procedure is a goal-oriented task, and steps in the instructional videos are performed sequentially. Also, the segments are annotated in non-overlapping fashion. Our work focuses on segmenting the individual steps and summarizing them in a natural text. The general pipeline is to extract the video features offline and learn the procedure segmentation via encoder-decoder network. Finally, a conditional language generation module called summarizer is used to summarize the segments. The procedure segmentation datasets has some variations in the annotation. Example, You Cook Too and Tasty has natural text corresponding to the segments as shown in the left, while other datasets like Crosstask or Coin has fixed labels as shown in the right figure. The natural text-based annotation of segments pose challenge in accurately evaluating the quality of estimated procedure segments. Let us discuss the challenges now. Consider a hypothetical example with ground truth segmentation, as shown in gray color box, and estimated predicted segments. We do not have label for each segment, and it is difficult to find one-to-one correspondence between ground truth and generated segments. To tackle this issue, prior work utilized proxy metric such as proposal detection and iterative matching. The core issue in such metric is the lack of temporal order to find the mapping between the ground truth and predicted segments. First, we discuss on how the proposal detection based metric works, and later we'll look at the issue. We compute the IOU between each ground truth and predicted segments. Here are a few steps in an animation format. Once we have filled the table, then we find the set of proposals and the ground truth which are greater than specific threshold, and finally compute the precision and recall. For example, with the threshold of 0.3, we have two proposals P2 and P4 in the proposals from the proposals, and the ground truth segments G1, G2, and G3. In this example, recall is 1 as the predicted proposal has full coverage to the ground truth segments. However, we argue this is incorrect as the ground truth G1 and G2 match with the same proposal P2, and we will use the single predicted segment to generate the summary, which can lead to inaccurate results. The correct recall should be 2 by 3 with G2 and G3 in the ground truth set. The alternative metric is to iteratively find the best match with highest overlap from the predicted proposals for each ground truth segment. For example, the proposal P2 is the best match as it has the highest IOU for ground truths G1 and G2. This will give inaccurate mean IOU. Again, this metric fails in considering the temporal order and one-to-one mapping of segments. The correct mean IOU should be 0.5 and map the proposal P1 with ground truth G1. To tackle the issues of these proxy metric, we propose an exact metric to find one-to-one mapping and also consider the temporal order of segments. We are inspired from the Saudacy metric, which measures the sequential captions considering their temporal order, and we propose the Soda D metric with a modified cost metric and a regress equation as shown. Our proposed metric finds one-to-one mapping and computes the optimal mean IOU for procedure segmentation. We show step-by-step computation of dynamic programming and traceback table. The algorithm adds the current IOU value to the previous diagonal element and select the maximum value from the left, top, and diagonal element. We also store the maximum value index in the traceback table. We repeat the steps and fill the entire table. Once we have filled the traceback table, then we find the matched pairs. We start from the bottom right corner of the table and select the matched pair based on the first encountered cell labeled with diagonal index. Using the matched pair, we compute the precision recall and F1 score to accurately evaluate the over and under segmentation of procedure in instructional video. We compare the existing overlap-based metric with our proposed metric. We use three uniform baselines. The first one uses average number of segments in the video across the dataset. The second one uses average duration of segment in the dataset. In third baseline, we assume that we know the ground truth number of segments and divide the video uniformly. We also show two competitive methods, ProfNets and PDVC. This table shows that the mean IOU overestimate the method's performance. We also found that the recent techniques developed for PSS perform worse or same as the uniform baseline on the proposed evaluation metric. To further investigate the low SORA D score, we look at the modules used in recent state-of-the-art method, that is PDVC. The Hungarian matching module in the pipeline is a potential bottleneck for the lower SORA D score, as Hungarian matching algorithm does not consider the temporal order of segments for further processing. To improve the performance, we propose to replace Hungarian matching algorithm with our matching algorithm used in evaluation metric. Additionally, we propose the differentiable version to train the pipeline in end-to-end fashion. To make the matching algorithm differentiable, we convert the IOU maximization problem of matching algorithm into minimization by negating the cost and replacing the max operator with min operator in the recurrence equation. Further, we replace the non-differentiable hard min operator with smooth min operator. We compare results on two datasets, UCook2 and TASTY. First, we use three uniform baselines. We also use two competitive baselines, ProfNets and PDVC, which uses Hungarian algorithm. We also explore video features and found that features extracted from S3D model, which is trained on multimodal objective, performs better than simple image-based features. This improves the state-of-the-art by 4.75% on UCook2 and 4.1% on TASTY. We further enhance the performance with our proposed matching module by 3.7% on UCook2 and 3.8% on tasty dataset. Here are some qualitative results. Our method improves the segmentation quality and reduces the redundant proposals. In summary, we identify the issues in current proxy evaluation metric for procedure segmentation. To address such issues, we propose new metric SODA-D, which considers the temporal order and one-to-one mapping. We also propose the differentiable version of our matching algorithm in the training pipeline to improve the quality of procedure segmentation in instructional videos. We use the two datasets UCook2 and Tasty and achieve state-of-the-art results. Thank you. For more information, please check our paper.